everyone. Today in our seminar, Helena Šmigoc is going to tell us about symmetric nonnegative trifactorization.
Thank you. First, I would like to thank for the invitation to speak in the seminar. And I'm going to talk about symmetric nonnegative trifactorization, and this is work that's coming from the joint work with Damiana Kokol-Bukošek from the University of Ljubljana. To start thinking about motivation, or to start thinking about factorizations that the type of factorization I'm going to be talking about, I have here some decompositions. On the left, we have classical decompositions that we teach to our students. And on the right-hand side in blue, we have in parallel factorizations, where we're starting with a non-negative matrix. And here, by non-negative, I mean entry-wise non-negative. So all the entries are greater than or equal to 0. And we're looking for factorizations where we are requiring factors to be non-negative as well. If we start with singular value decomposition, we know that any matrix, so here we can reduce ourselves to real numbers, but we can also think about complex numbers if we want, can be written as U sigma V transpose. So here, my point is that we don't have any particular restrictions on the matrix, and we can find singular value decomposition. And singular value decomposition plays an important role. In particular, we want to approximate matrix with a low rank matrix. In parallel to this, we can have a non-negative matrix factorization, where we now want to write a matrix A as a product of two non-negative matrices, W times H transpose. And typically what we want to do is minimize the number of columns in those matrices, W times H transpose. And again, we have sort of a low rank interpretation of this matrix in this case, but in a different way. Moving to the second row, there we have we're starting with a symmetric matrix, and if the matrix is symmetric, then I can write it as a product U du transpose over real numbers. I'm thinking now, where D is diagonal and U is orthogonal. And that direction works as well. So if I'm looking at the product U du transpose, I don't have to compute the product to know that my matrix will be symmetric. So we would like to start with a symmetric non-negative matrix and look at factorizations where the factorization will respect symmetry in some sense. And this brings us to the trifactorization that I'm going to be talking about. So it's called SN-Trifactorization, symmetric non-negative trifactorization, where we write a matrix as a product BCB transpose. Here we require matrices B and C to be non-negative, and we want C to be symmetric as well. And as we've seen in spectral decomposition, if I see the product BCB transpose, I notice that this matrix will be symmetric immediately if I know the matrix C is symmetric. And of course, it's also non-negative. And if the matrix C is K by K, then I know also the rank of the matrix A will be less than equal to. So it's kind of respecting symmetry and telling us something about the rank as well. In the last row there, we have Koleski decomposition. And here we know that the starting matrix needs to be positive definite in order for me to be able to write it as L times L transpose in order to the Koleski decomposition to exist. And there's, in parallel to this, we can think of matrices that are called completely positive. And here the family of this matrix is actually defined through the factorization. So any matrix that can be written as a product BB transpose, where B is non-negative, is called completely positive. And necessary conditions for complete positivity is symmetry and positive semi-definiteness. But it turns out those are not sufficient, so it's a smaller class. Now that we have started thinking about these factorizations, our focus will be on the symmetric non-negative trifactorization. Let's first say something about non-negative matrix factorization, which is the most well-studied, I guess, of the three. When we are starting to look for the factorization of the matrix into the negative factors, our first stumbling block or first requirements that we need to be thinking about would be the restrictions coming from the pattern of the matrix. Here I can start with a non-negative matrix A, and and forget for a moment, forget the entries or the values on this matrix and only consider the pattern. And the pattern restrictions that are on factors W and H such that A will be equal to W times H transpose. I can study this pattern in a way that I want to factorize now 0-1 matrix in terms in the product of two other 0-1 matrices, and I'm doing operations over Boolean arithmetic to preserve 0-1 pattern. The smallest number of columns that I can obtain in such factorization is called the Boolean rank of the matrix, and it's associated with the pattern, not with the values. So the Boolean rank of A, denoted in this talk by rank with subscript 0-1 of A, is the minimal T for which such factorization exists. And here you see in green, Boolean rank 2 is exhibited in this factorization, right? So I can write this 4 times 3 matrix as 4 times 2 and 2 times 4 matrix, so we have Boolean rank 2 in this case. Once you understand the pattern, then we can start fitting values to this pattern, and those can bring additional constraints. So in general, the NMF rank, which is the minimal number of columns in the matrices W and H, so I can write the matrix A as W times H transpose, this rank is typically greater than the Boolean. So it's we have only a lower bound from the Boolean. Of course, all the factors here I'm requiring to be non-negative. Studying exact NMF is a nice theoretical question. The one that is most often encountered in applications is approximate NMF. In this case, we would like to approximate our matrix A with the product of matrices W times H transpose. And the essentially different idea here is that we decide on the number of columns that we want. So starting off, we decide the number of columns we want in matrices W and H transpose, and then we run the algorithm that gives us approximation, matrices W and H transpose that approximates this matrix A. But we don't get equality. And this idea was introduced by Patera and Tapper in 1994, and later popularized by Li and Sang in 1990. And since this paper in Nature that was published by Li and Sang, the NMF has seen a big has received a big attention in anywhere where we are analyzing non-negative data. NMF is playing, this approximate version of NMF plays a central role. All right, so this is the related factorization, but the factorization that I want to talk about is, as I mentioned before, SN-Trifactorization. And in this case, I'm starting with a symmetric non-negative matrix, and I would like to write it as BCB transpose. And I will be now talking more from theory point of view, not so much application, so I want exact factorization. And what I would like to do is I would like to find the minimal possible size of the matrix C in the middle, so or equivalently the minimum number of columns in the matrix B. This minimal possible K in such factorization is called the SNT-rank of the matrix, is the stope denoted by ST class of A. So as an example, in green, we see a 4x4 matrix factored as 4 times 2. So this will be the first matrix is B and then C and B transpose. So this factorization is exhibiting SNT-rank 2. And that is actually the rank. SNT-rank and actually the rank of this matrix as well. So this is the type of factorization that I'm studying in this talk. There's also an approximate version of SN-Trifactorization. And this is before Damiana and I started working on this. This is actually the only one that was studied in the literature. And like we've seen for the NMF, we are starting with symmetric non-negative matrix, and we would like to approximate it with a product BCB transpose. Here, the reason that approximate SN-Trifactorization plays a role in applications is that the columns of B, so we start with some items, and the relationship between items are recorded in our data matrix A. The Trifactorization then identifies communities in the columns of the matrix B, and that means highly correlated items in the data set. And the matrix C tells us how those communities interact with each other. So that's the interpretation behind this factorization, at least approximate version. Our focus today will be the exact one. So we would like to write matrix A as B, CBB transpose exactly, and we're looking for smallest K in which such factorization exists. So call in SNT-rank or denoted ST plus of A. First, let us compare this parameter to other ranks that we know or heard about. The normal rank, SNT-rank of A, is always greater than or equal to the rank of A. That's not surprising. And it's also easy to see that's less than or equal to n, because A can be trivially written as identity times A times identity, and that is SNT-Trifactorization, but not often optimal. If the rank of the matrix A is 2, then SNT rank is also 2. So here we have equality. It's true for rank 1 as well, but it's a little bit more interesting for rank 2. But this nice relationship already drastically fails when we're talking about rank 3 matrices. Because even for rank 3 matrices, we can find matrices that have as T plus of A as big as we like. So of course the matrices will have to be big in that case, but we cannot bound SNT rank independent of n. So it has to be just with the rank of the matrix, we cannot bound the SNT. How about NMF rank? How does SNT rank compare to the NMF rank? Is greater than or equal to NMF rank because the factorization BCB transpose is more restrictive than just W times H transpose. But it can never be bigger than 2 times the NMF. In some situations, the 2 ranks agree. There are several versions of NMF studied in the literature. One of them is called separable NMF. And in this case, we're looking at factorization where the first matrix W consists of columns, of certain columns of the matrix A. So we permute our matrix A so that we have some submatrix consisting only of columns of the matrix A as a first factor. That's called separable NMF. And once I see such factorization, then with K columns in the matrix in the first factor, then I know that SNT rank of A will be less than or equal to K. That can be proved. So in this case, the ranks are closely connected. But they are different. And this is the smallest example that Damiana and I were able to find. Here we are starting with a 4x4 matrix and written as 4 times 3 and 3 times 4 non-negative matrices. And this exhibits NMF rank 3. So the matrix is rank 3. So we know that this matrix has NMF rank 3 as well. And now we can start looking for an SN3 factorization that would also exhibit NMF rank 3. Now, what we see here in green is what we can do without loss of generality. I won't explain how we arrived to this pattern, but a lot of it has to do with these 2 zeros that appear in the matrix A that restrict a lot of the entries in here. Without loss of generality, we can restrict on this green pattern we have here. And then once we start multiplying things together and look at the entries that would need in that would need non-negative, we get a contradiction. The reason I'm showing you this example is not only to show that the 2 ranks are different, but also to show you how the interplay between the pattern and the values comes in. So here, this example, I wouldn't be able to complete based on the pattern alone, although the pattern played an essential role for me to be able to determine the SNT. So the values and pattern kind of worked together for this example to work. And from now on, I will now concentrate on the pattern because this is a graph theory seminar, right? So I decided to put more graphs in here. So I will concentrate on the pattern only. Like we see for the NMF, we start with symmetric non-negative matrix. And from now on, we will be only interested in the pattern of this matrix. So instead of the non-negative entries, we can restrict ourselves to 0-1 matrices. And we can record the pattern of these 0-1 matrices by graphs. Represent them with graphs where we have an edge in the graph if Aij is positive. If and only if Aij is positive. Now, I should explain that what we get is a simple graphs because we have symmetric matrices, but we are allowing loops. So simple graphs with loops, because in this case, we do want to understand what's going on the diagonal of the matrix as well. So in this example, we have a 1 in a 1-1 position, and that means my vertex 1, that's a loop. And that is important to understand that in the factorization. Starting with the graph, I can study the set of all matrices with this given pattern, and I call the set ST plus of G. So ST plus of G contains all non-negative matrices whose pattern graph is this given graph G. And the parameter that we want to understand is the minimal SNT rank among all matrices in this family of matrices. So I'm looking for all of the matrices that have given pattern graph, and I want to know what is the minimal rank that these matrices can achieve. That is called SNT-rank of G, denoted by ST plus of G. To study this parameter, I need to introduce an idea of set joins. Now, joins are a very common object in graph theory, and this is sort of a very related concept. Set join is a graph where a vertex set is contained of two different subsets of a given finite set S. So we are looking at sets K and L, and basically we can think of the vertex set just to be the union of K and L, although more generally we can make it a bit bigger, but that would introduce isolated vertices. The set join of K and L is therefore a graph where we have an edge in the graph Ij if I is in K and J is in L. So all the edges, we have one vertex in K and one vertex in L. So this is very similar to complete bipartite graphs, except that the vertex in both sets, K and L, then this vertex is connected to all the other vertices, including itself. So here in this example, we have sets 1, 2, 3, and 1, 4, 5. So if I removed one, I would get complete bipartite graphs to K to 2. But adding one brings me this one that's connected to everything, including itself. So that's what's called set join. And now to another common idea in graph theory, which are, before we do that, let me explain some familiar examples. Stars are set joins, in particular, where one of the components in the set join, one of those sets is a singleton, then we get a star, or complete bipartite graphs I mentioned already. If the two sets are disjoint, then the set join is just complete bipartite graph between those two sets. The objects that we want to study are called set join covers. So now that we understand what set joins are, I can start with a simple graph with loops like before. So the graph associated with the pattern of some matrix, perhaps. And I would like to cover all the edges in this graph with different set joins. If a collection of set joins covers all edges of a graph, then I call this a set joint cover of G. And for every set joint cover of G, I can define the corresponding new graph, C of G. Now the components of this graph are just the sets that appear in set joints. So if my collection is of set joints is Ki join Li, then the vertex set of this graph, C of G, is just those sets, Ki and Kl, the union over all of them. The order is the number of elements in this component set, and the edges are defined in perhaps a natural way. If Ki and Kj are an edge in this graph, if and only if Ki is joined to Kj in my component set. So if Ki joined Kj appears in the set join cover, so then that we have an edge there. How is all this connected to my SNT-rank of graphs? Well, it turns out that SNT-rank of graphs is the minimum over minimal number of these components that I need to get a set join cover of G. So the optimal set join cover of G, so what I'm minimizing, I would like to emphasize here, is not the number of elements in the cover, but the number of components that I needed in the cover, right? So the cover is the selection of set joins, and then these set joins have different components appearing. And what I would like to minimize is the number of components. Why are those two things different? Because the same component can appear in several different set joins. So then we will have maybe the component set will be smaller than twice the number of elements in the set join cover. Right, so this is the minimum. This is the parameter that I want to minimize because that's the one that gives me the SNT, the graph. For the covers that have the minimal number of components, I call those covers optimal. So I call them an optimal set join cover, or in this talk from now on, it will be just denoted OSJ covers, optimal set join covers. So the ones with have the minimal number of components. I have introduced quite a few definitions. So here I have a very baby example to get those definitions illustrated on a small example. So here we have a graph that is covered by, in the picture, I'm trying to illustrate two set joins. And in this case, they're just stars. I have component 1 to 4 that's joined with component 3. So that gives me the star with center vertex 3 and covers the orange edges. Then I have another set join with components 3 and 3, 5, 6. And this is the star with the center vertex 4 and green covers the green edges. And so I have gotten the set join cover of my graph. This set join cover has 4 components, K1, K2, K3, and K4. So the number of elements in the vertex set of this cover is 4. And this turns out to be the minimal number that I can have, the minimum number of components for this graph. So SNT rank of this graph is 4. The graph of this set join cover is 2K2 because here I have 2 independent edges. You could think K1 is joined to K2 and K3 is joined to K4. So I have 2 independent edges. The graph is 2K2. And to connect back to factorization, this is trying to show here with the colors a little bit. In the B, every column of B corresponds to a different component. So in the first column, I have blue. In blue, I have vertices in positions 1, 2, and 4, and that corresponds to having elements 1, 2, and 4 in the component K1, and so on. And C is telling me how these components are joined. So K1 is joined to K2, so I get this 1 entry in 1, 2 position, and K3 is joined to K4, so I get 1 entry in 3, 4 position. And once I multiply these matrices together, I get the pattern. I get a matrix whose pattern is exactly the graph you see in the picture. Here I have another set join cover, and this one is also optimal. What I have added in the second one is just one other set join where we add join 3 to 4. So that means that this edge 3 to 4 is covered for the 3rd time. I could have, by adjusting the components, I could achieve maybe on having this edge only covered once, but I don't, in my optimization problem, I don't mind if an edge is covered more than once. So C1 is another optimal set rank cover, and with the same component set. So again, we have number of components 4, but a different graph, because in this case, K1 is joined to K2, K2 is joined to K3, and K3 is joined to K4. So the graph of this set rank cover is P4. So you see that there are two different set rank covers for this simple graph, both optimal. To get us even a little bit more familiar with this idea, let me talk about interpretation of this that you can think about. Let's say we have a set of items that are either forbidden or required to interact. And we report these restrictions in a graph. So if two items are required to interact, we put an edge between them. And if they're forbidden to interact, then there's no edge between those two items. And now we would like to organize these interactions by certain meetings of subgroups. And if the two subgroups meet, then every item from the group K interacts with the item from group L. So if the two items are forbidden to interact, then there can't be one, it can't be group K and the other in group L if K and L meet. So that we need to avoid that. And the optimization problem that we are thinking about is what is the minimal number of subgroups that need to be formed to be able to organize these interactions in such a way that no forbidden interactions occur. So again, I'm not optimizing the number of meetings. I want to minimize the number of subgroups that I need to form. And that gives me my SN-T-rank. Already here in this example, I try to allude to the idea of uniqueness, right? So here we've seen two different set rank covers with two different graphs corresponding to the same number, or actually corresponding to the same components and corresponding to the same graph. But we can also think about uniqueness, and there's actually three different concepts that we have studied. The first one is the one we just say unique optimal set rank cover. It has to be that one, precise one. So there's unique cover of the graph. But a lot of the time we're thinking of graphs that have a lot of symmetry, and then it makes sense to think about essentially unique OSJ covers. And those are unique up to automorphism of graphs. And finally, the weakest form of uniqueness is just the unique OSJ cover graph. So the two covers may not be unique, that there's no automorphism between them, but they might have this isomorphic graphs, and that's another way. That's another way of understanding uniqueness. The most restrictive one, of course, is the unique OSJ cover, and the least restrictive is unique OSJ cover graph. The parameter ST plus of G behaves well with respect to certain operations. The one that once you start thinking about this, you notice immediately is that this graph, this parameter behaves well with respect to duplicating vertices. So if I take a vertex and duplicate it with the same neighborhood, then I will not change the SN-T-rank. So this is written formally here in the way that two vertices are called twins if they have the same neighborhoods, and the graph is twin-free if no pair of vertices are twins. And SN-T-rank of G is the same as SN-T-rank of the biggest twin-free subgraph of G. And it turns out that the uniqueness is also preserved. So G has unique OSJ cover if and only if the biggest twin-free subgraph of G is. Idea why would such a thing be true is very simple, because if I have a twin and I just put the twins in the exact same components, then I will be covering the edges those twins are involved in. So, from the construction, it's not very difficult to see. But what we can do with this, once we see this, we can restrict our analysis to twin-free graphs. So we can just remove twins and just think of twin-free graphs. Another operation that we can understand completely from the point of view of SN-T-rank is adding a vertex, join with the vertex. So I have a graph and I'm adding another vertex, and I connect it to every vertex in the graph G, and I add a loop to that vertex. And if I do that, then I haven't changed the SNT-rank graph, except if my starting graph had some isolated vertices, then I have increased the SNT-rank by 2. But if G had no isolated vertices, then this extended graph has unique OCJ cover if and only if our static graph G had. An idea in the proof again here is not very difficult. I can add this new vertex to just all the components that I see in. Let's say that I have an OCJ cover of G, so I have certain component set. I just toss this red vertex in all the components, and now I have and extend the cover in a natural way, and I have covered these new edges that I have introduced as well. Again, except in the case when I have isolated vertices, where I need to take care of those separately. Turns out that graphs that correspond to optimal set-join covers have a particular properties. For example, their SNT rank is equal to the SNT rank of the graph. So the SNT rank of the optimal set-join cover is the same as the SNT rank graph. These graphs are twin-free. We can probably see this from what I said before and from this observation. And the third bullet point I find the most interesting is that the graph G contains a subgraph that is isomorphic to C of G. And that is useful when you try to come up with a certain factorization. So this observation restricts the pattern of this matrix C in the middle with the factorization, but also tells us that if G has monotone property P, then C of G will also have the same monotone property P. So monotone property means that monotone properties are properties that are preserved with subgraphs. So if a graph has a property and every subgraph has this property, then this property is called monotone. Example of such properties as graph is acyclic, triangle-free, bipartite, and so on. So, and these properties are preserved from the graph to the graph of the optimal set-join cover. And now I want to talk about some specific families of graphs, starting with trees, where you will see the answer is very simple. And the second example I will show you is the complete graphs without loops, how to find optimal set-join covers for those, or at least tell you something about that. Starting with trees. Because trees have no cycles, we are actually restricted to covering with stars. So here we can study stars and covers with stars independently, whether we're talking about tree or not. Starting with a simple graph without loops. Here I don't want stars to have a loop, so that means that vertex V is not in K. I can try to cover my graph with stars, and then I will get edge star cover. So I want to cover all the edges in my graph with those stars. And edge star cover number is the minimal number of stars I need to cover my graph. So that's a well-studied concept. It's not ours. But every star introduces two components, the central vertex and then the neighborhood. So this inequality is true in any graph. St plus of G is less than equal to 2 times the star cover of G. But for trees, this is an equality. So if it's a tree without loops, then the St plus of T is 2 times the star cover number, edge star cover number of T. The way you would see this, you would start with a tree, and then you would think about a leaf, and you would say, okay, I need to cover this this edge coming from a leaf to the center vertex somehow. And soon you would see that then this blue vertex has to be the center of the star. And then you might as well, without loss of generality, toss all the neighborhood of that vertex in the component. And now we have covered all the edges in that star, and then proceed inductively. We can decide with a little bit more argument, we can decide the uniqueness here as well. T has unique OCJ cover if and only if the distance between any two leaves in T is even. So we can decide when we have uniqueness. But what is maybe even more remarkable is that here, actually, all of these parameters that we were thinking about are constants on the whole family ST plus of T. Starting with any non-negative matrix, now it can have any values it wants, then the rank of this matrix is equal to SNT-rank of this matrix, is equal to SNT-rank of the graph, and it's equal to twice the edge star cover number of the tree. Okay, so here we have a complete answer. We can not only for the pattern, but for any values we can add to the matrix. So stars in some sense, trees in some sense are the one side of our complete graphs, right? So here I had two examples. On one side I had trees, and now we understand the trees, and now we will move to the complete graphs without loops. So I'm not gonna talk about loops. And to understand what's going on there, I need another concept. I need to introduce the concept of separating cover. We're starting with a set of n elements, just call them 1 to n. And we look at collection of subsets of the set 1 to n. Let T be such a collection, and we call T a separating cover of the set. Even for any pair of elements, ij in 1 to n, I has to be different from j. There exist sets A and B in my collection, so that I is in A and J is in B, but A and B are disjoint. An example of a separating cover of n elements is given here. So in blue, we have sets 1, 2, 3, 4, 5, 6, 7, 8, 9. And these sets separate all the elements 1 to 9, except the ones that appear in the same set. So 1, 2, and 3 are not separated. For that, we need to introduce 3 more sets, and these are here in green. So here I write 1, 4, 7, so I go in steps of 3, 2, 5, 8, and 3, 6, 9. And note that now these elements 1, 2, 3 are now in 3 different sets, 1, 2, 3, so they're separated. And turns out that this is the minimal number of sets needed for me to be able to separate the set with n elements. And this is actually unique. This is in the minimal case, this is unique. How is this connected to our set joints? Well, if I have a set joint cover of a complete graph without loops, then the component set of this separating of this cover will be a separating cover of L elements with V of C sets. Why? Well, because I need to cover every edge. So all the edges are there. So I need, for every pair of vertices, I need to have a set K and L that I is in K and J is in L. So that will cover the edge IJ. But because I don't have loops, that means that these sets K and L will have to be disjoint. So I get in a natural way to the separating cover. Okay, so the minimum number of sets in a separating cover of n elements is equal to ST plus of Kn. And back to the example that we've seen before. So here we have a components given, and then in the cover, we just put all the joints we can. So remember, we can't join two sets that have a non-empty intersection. If I join K1 with L1, then I would get a loop on the vertex 1, and I don't have that in my graph, so it's not allowed. Right, so now we're looking for the minimum number of sets in a separating cover, but turns out this is not a new question. It was posed by Katona in 1973. He asked, what is the minimum number of sets in a separating cover of n elements? And now we know this is the same as asking for ST class of Kn. Not only the question is not new, also the answer is known. It was found independently by Yao in 1976 and Kai in 1984. And they gave us an explicit formula. So we have exact answer here as well. This is the formula for SNT-rank of Kn. You can look how this behaves on small examples and so on. But maybe what's interesting to us is to compare this now with the Boolean rank of Kn, which is also known. Because Boolean rank of Kn is known, we can determine its asymptotic behavior in this 1 over log 2 times log n. And from this formula here, we can also determine asymptotic behavior of SNT rank, which is 3 over log 3 of log n. So both of those parameters behave as log n, but the constants are different. And this is another illustration that these ranks are actually behaving differently. They're different parameters behaving differently. Here I have the same parameter, so SNT-rank of Kn, written in 3 different ways. The one in red we have already seen, and this is just explicit formula, right? So it has 3 cases depending where n is. The last one is recursive formula, and that comes from the proof, which is inductive. So the proof is inductive and kind of allows us to go from the bigger graph to the smaller graph. But what I find maybe even more interesting is this one in blue, which gives us interpretation of this parameter coming from number theory. Imagine we have a number n, and we're looking for integers, qi, such that the product of these integers is greater than or equal to n. But what we want to do is minimize the sum of these integers. And turns out the sum, the minimal sum, is actually equal to the SNT rank of Kn. So that's how we, that's the same parameter as well. You will get a little bit of insight in why this might be in the last few minutes that I have in this talk. Let's write n, and let's say that I have a number n that can be written as a product of 2 other numbers, p and q. They don't have to be primes, just I factorize n as p times q, both of them greater than or equal to 2. And then I would like to find a cover, separating cover of these n elements, or set join of Kn. And I do exactly what you've seen previously on the 9 by 9 case. I have these blue sets and green sets. Blue ones, I go from 1 to p, and then from p plus 1 to 2p, and so on. So I just write consecutive numbers, 1, 2, 3 to p in one set, and then p plus 1 to p plus 2, and so on. These are my sets, ki. And then LJs, in LJs, I go in steps of p, starting with 1, 1 plus p, 1 plus 2p, and so on. And as we see in the 9 by n is 9 case, the blue ones already do a lot of separation, except they don't separate the numbers that are in the same set, right? So 1, 2 to p are not separated, but they appear in different sets in the L numbers, in the L sets, 1, 2 to p. So the first column will separate the elements in the first set, K1. The second column here, 1 plus p, 2 plus p, 2p will separate the sets in elements in K2, and so on. Cover, like before, will be join all the Ks together, join all the Ls together, and we'll get a set joint cover of Kn. With components, number of components is just Kp plus Kq. That illustrates that SNT rank of Kn is less than or equal to p plus q. And we can iterate this, and this is how we then get back to here. And it turns out the best factorization we can get if we factor n as a power of 3. So it's 3 by 3 by 3, then we get the sum minimal possible. That's how it's the connection to the minimizing that number of components. We can formalize this even in more general setting. Very similar idea works for conormal product of graphs. So conormal product of graphs G and H is a graph with the vertex set V of G cross V of H, where 2 vertices are connected. If G is either connected to G prime in G, or H is connected to H prime in H. And this is the inequality that can be obtained by extending the SNT by set-join cover in similar way that we see in graphs. The last thing, so with Damiana, we were studying this rank, SNT rank, for a while before we noticed the result is already there. So what we did, we studied the proof and analyzed it, how it works, and also we were able to determine the uniqueness in that case. So we can determine when the OCJ cover is essentially unique. So in this case, only essential uniqueness makes sense because the complete graphs have so much symmetry. So we have K6 has essentially unique OCJ cover, but K4 has two essentially different OCJ covers. The SNT rank is 4, so we can't reduce it at all, it's 4. So one cover we get where all the components are singletons, but we can also get a cover where 1, 2 is joined to 3, 4, and 1, 3 is joined to 3, 4. Other examples of essentially OCJ covers for Kn are where n is either the power of 3, 2 times the power of 3, or 1 off. So n is the power of 3 minus 1, or 2 times the power of 3 minus 1. So we have decided SNT rank for trees, and we have found that solution already exists for SNT rank for complete graphs, and we introduced the framework for studying this parameter, but there's still a lot to do. We haven't really studied loops that much, graphs with loops, how that would have to optimize and what kind of approaches we can have there. And we have published our work in 2 papers. The first one, Symmetric Nonnegative Matrix Trifactorization, I didn't really talk a lot about today. This one is studying the SNT rank of matrices, not of the patterns. So its results more on the rank of the matrix. And the second, Symmetric Nonnegative Trifactorization of pattern matrices, you can find on the archive. And this is where we study patterns, and most of my talk today was about that. So thank you for attention.
Thank you very much for your talk.